All right, so welcome everyone to this second session on the system design. This is essentially following the first session that we had about a week and a half ago. And then what we'll do is today we had a bunch of slides last time that we couldn't cover. So Naga has actually agreed to have a follow-up session, and let's get going with this. The goal of this session is essentially to share some of these core design topics that are crucial in interviews. But that being said, if folks actually have any questions or concerns, feel free to use the chat forum, and you should be able to hear us. And that's about it. If you're dialed in from your computer or your phone, please be on mute as much as possible and only unmute yourself when you're speaking, because that's probably the best way to. Otherwise, you'll be disturbing the audience or the conversation. I will be putting you on mute if I hear a bunch of noise from your side. So please let me know if you want to be unmuted. All right, so that's all I have. Let's get started. Naga, on to you.
Yeah, thanks for the intro, Vivek. Hi guys, welcome to the system design session 2, and I will go through which all topics that we are going to cover in session 2 in a minute. So I think this will be helpful even if you haven't attended the session 1 earlier, because these are all standalone topics mostly. And yeah, and if you have any questions, feel free to ask as and when you get it, or towards the end. Okay, with that, let me go to the topics that I'm going to cover today. So the left hand side, whatever you see, it's already covered in session 1, and you can actually find the link in the meetup. That's part 1, and the one on the right side is what I'm going to cover today. So if you have looked in the previous slides, I didn't have the consistent hashing. I added that, and that's very important concept too. We will get to that. We'll try to wrap this up within an hour and a half, and then I can possibly cover that. If not, the slides are good enough for you to get an insight, or I'm also happy to cover that in another follow-up sessions. Okay, with that, let me get quickly to the topic. Oh, sorry. How do I go back? Okay. So the first topic that we are going to cover today is the proxies. So with knowing or without knowing, most of us, when you're using some service on the internet, or even browsing, you might be going through some proxy servers. And we will see what it really means. So a proxy server is any server that sits between your desktop and the actual target server. Could be any intermediate server, and the main purpose of that proxy server is simply to forward your request to the target server and get the response and pass back to you. And there are 3 different types of proxy servers. One is a gateway, which is not really categorized as a proxy, but if you are just want to do some tunneling of TCP, port 80 or 443, you just don't want to forward to your have users directly call you, you can route through some gateways or tunneling proxies. That job is just plain request forwarding and response receive and forward back to the clients. And the second type of proxy is the open, and it's also called forwarding proxy. And the third type of proxy server that we are going to see is reverse proxy. Since there is not much to cover in gateway, it is a simple proxy. I will not going to talk about that much. We will jump on to the open proxies now. So so this open proxies, the name it says like it sits anywhere like in the internet, not like within your organization or something. Like it's this is a proxy server which sits anywhere in between in the internet, and your desktop could be anywhere in the world connecting to the internet, and similarly the target. So such proxies are called open proxies, and these are further classified into two types. One is anonymous proxy and the other one is transparent. The name mostly
Naga,
says...
quick question. Are load balancers also proxies? That's a question on the chat.
A kind of proxy, because like because you're not directly talking to the servers, right? Like all the clients know is the load balancer's IP, because it's invisible to the it's not known like to the user. Like yeah, it's also kind of proxy, I can say, because it routes requests to the actual servers. So that's a different type of functionality altogether.
Makes sense. Carry on.
Mm-hmm. So I mean, like this proxies, when I say it's like when we say open proxies, the user is aware of that he is being routed through the proxies, like when we say open. So there are like two types of proxies, as I said, like anonymous and transparent. So anonymous, as it says, like it doesn't reveal its IP address, nor like it also doesn't disclose the user IP address to the target server. So I mean, like this is useful when like you do not want to disclose the identity. So it's beneficial for users if they want to hide. So transparent, as the name says, like the IP address can be seen. The proxy itself, proxy server itself identifies it as being transparent, and like one thing is like sometimes if you are going to access some secure like maybe government or that kind of websites using, I mean, like this kind of proxies, it might your IP might get banned. So with that, let's move on to the next proxy, which is important, like the reverse proxy. So this, I mean, like the main purpose, it also actually forwards the request to the servers. The main difference is that it doesn't sit anywhere on the like in the internet. It sits as close as to your organization, like or your servers, or like web servers or application servers, or close to your database. Like it sits mainly within your organization boundary and as the first entry point. So as you can see, it clearly in this picture, it shows like the internal network. So the benefits it adds is basically like it hides all the backend web server information. I mean, like though you have like 5 or 10 web servers or application servers, like all the clients, whoever accessing the service is only aware of the proxy IP address. So like it's all hidden, and it can protect your, I mean, like internal servers from DOS and DDoS attacks. If you don't know what DOS attack is, like it's a denial of service and distributed denial of service. And what happens in that attack is like imagine if you don't have this proxy server, and if you are directly given like the clients directly or web server how they want to access like the IP and all. So some person who is like some competitor or some hackers, they can make illegal use of this information and directly increase the load on your server, like hitting random requests, and they just want to prove that your web server could not handle the actual legitimate request. So thereby preventing your business from growing. So this having a reverse proxy can prevent such attacks also. So, and like another security aspect is if your web servers don't offer any basic authentic or any form of security, this reverse proxy can add one layer of security, which is like basic authentication. If you're aware of like HTTP basic authentication, it actually works with username and passwords. So having reverse proxy also increases the flexibility, and you can scale up and down behind the scenes, because even if you add like 2 or 3 web servers or application servers, it's like not known to the clients. And it can do SSL termination. That means like if for the internet, like for the clients, all our URLs can be HTTPS, so meaning like it's all encrypted. Since anyway we are in the internal network, I mean like it's all secured zone, all our internal communication between the proxy and web servers can be like without HTTPS, like a plain HTTP. So that increases actually a bit of performance. So that is one functionality that reverse proxies can add. And so and if your server responses are quite big, reverse proxy can do some kind of compression. And another benefit is like it can cache the responses, and also it can cache the static content like HTML files, JavaScript, and all the audio, video kind of content, images.
Hey, Naga, one quick question from Martin is that is there like a performance concern when you use proxies, because there's an additional hop, right? So would there be additional latency or increase in latency because of a proxy?
It actually adds like one hop, but if looking at the advantages, like if you don't have like the benefits that you are seeing of the reverse proxy that it offers, if there is no legitimate use of this benefits for your use case, then you might as well have all this security handled within your web server, and you can directly have the web server exposed to the internet. I mean like, so if you don't have a reverse proxy, which means that you are adding all this complexity directly into your web servers. So though you say one extra hop, I mean like you are...
Is that an extra hop? The answer is absolutely. But usually that extra hop is going to add like 10, 15 or like around 20, 25 milliseconds at most. And it is generally negligible compared to all the other challenges that you normally have. So absolutely worth that, like it's worth paying that 15 to 30 millisecond price to get all the benefits that you have. But yes, it is definitely an extra hop. And will it also be a single point of failure? Now that you have a proxy in the front, is it not a concern for you that it will be a single point of failure?
Yeah, it will be a single point of failure if you have only one reverse proxy. So I mean like I will talk about that in the drawbacks in the next slide. So, and though you are saying like one extra hop, like if you look at the caching benefit, right, like it can cache all the read-only responses like from the web server, thereby offloading some of the load on your web server. So your web servers can actually serve some true, I mean like genuine requests. Like, I mean like it can serve more requests, like if you leverage caching functionality within the proxy. And actually wanted to talk about this A/B testing. I'm not sure how many of you are aware of that. Like if you have 2 different versions of web pages in your website, and if you want to test which one loads better or which one takes how much time, or that kind of variation, multivariate testing, then reverse proxy can also do that. So with this, like I'll jump on to the drawbacks of reverse proxy, which is like actually since you are adding one layer, like one hop, like it increases the complexity. And as I said, like the single reverse proxy is again a single point of failure. So you would end up configuring multiple reverse proxies, so which further increases the complexity. And if you compare with load balancer, whether you want to go for a load balancer or reverse proxy, the general idea of load balancer is if you have your all web servers doing the same functionality, like they're just all the replicated nodes serving the same functionality in all the servers, so then load balancer is mostly like common way to use, because it's good at serving routing. All it has to do is the routing. And the reverse proxy can be useful even if you have just one web server. Like you can leverage all the benefits, and as shown in the previous slide, because like the main intention of introducing reverse proxies here is to prevent some abusive requests and from overloading your web server, because if somebody is trying to hit your web server and make it hard for the web server to serve some legitimate requests like the DOS attacks, then like in those instances reverse proxies can be really useful, and they only forward the request only when it is legitimate, and if you also have caching only for the write and some legitimate read requests.
Hey Naga, quick question. Do you normally use just a reverse proxy, just a load balancer, or a combination of both reverse proxy and load balancer? And if so, which one would you put in the front?
We can do both. And actually, if you look into this, the famous open source servers, I mean, like Nginx and HA proxy, they support both. I mean, like they can be used for reverse proxying. Also, they also do the load balancing. So, I mean, like it's how you want to configure. Like if you take HA proxy, whether you want to leverage only on reverse proxy benefits, or you also want to do some of the load balancing there. So it's kind of both. Like if you are having multiple web servers, like even though you have reverse proxy, you still need to end up doing some load balancing between the multiple servers. Only if you have one web server, then like it will be the true reverse proxy. And if you have multiple web servers, it will be kind of reverse proxy plus some load balancing functionality. So that's why mostly this like the top use like HA proxy and Nginx, they kind of support both.
Understood. Got it. Thanks.
So no questions. Like I'm ready to jump on to the next topic. Okay. So the next topic that I want to discuss is the databases and how we want to scale databases. So like with the databases,
Naga?
I'll first cover.
Yeah. So
Yeah,
you were talking about legitimate request, right, with the reverse proxy. So how does it determine whether a request is legitimate or it is a DOS attack?
So yeah, I mean like that's a good question. So this reverse proxy, like when we say it has some patterns, right? Like whether it's, I mean like it watches, I mean like some requests could look like legitimate, but though they are like intention that to overload your server. So they keep watching on different patterns using which I mean like people I mean like it's basically your reverse proxy will have all the best practices. I mean like to determine, they can look at your payload to understand if he is really a user. It can have some filters, like some watches, like if he is a fraud user, what would you do? He would have the same request and simply manipulate one or two request IDs every time. So it'll kind of watch for that kind of a patterns and filter out. And suppose another way to reduce is like for a user, typically if he's making some edit or update operations, or he would not make like 100 or thousands in a second or something. So based on our business design, like the general idea of the user's load, if we know that we definitely can't get more than 100 per day, so then we can have that 100 limit per user within the reverse proxy. So if that request exceeds the 100, then it's going to not allow to pass to the web server.
So are you saying like it is not like a common functionality, that firewall kind of functionality that is available on the machine itself? Is it something we need to code every time?
Not code. It's kind of a configuration in reverse proxy. So suppose like here you can have this configuration saying that for a user don't exceed him sending more than 100 requests. And it can also have some information looking into the HTTP header. I mean, like some kind of content. If you know, like at front you can determine, right, like what kind of requests can be falsify, or so if you know that kind of pattern, you can have that configuration done in proxy, and that proxy can determine for those patterns of requests and discard it here itself.
So
and even if we
have some template kind of configurations where like you can set as per your needs.
Yes, I think that will be possible in reverse proxy. So one is the limit the number of connections, and it can also look into some of your application layer to request parameters and determine if they are genuine parameters. Like, I mean, like if you notice some patterns, though you don't have it at the first place, if you keep noticing some, as and when you notice some kind of false request, you can actually keep updating the reverse proxy configuration for the next time, so it doesn't pass that request. So even if it passes to the web server, it I mean, like sometimes it can like if you do some offline analysis, it can know that this is not a valid request, or it could, based on some business rules, it could even fail. So we can keep watching for those patterns and have reverse proxy configuration, keep updating as and when you notice such things.
I see. Okay, thank you.
Okay. So let's go back to the databases. So yeah, I mean, like first we'll start with RDBMS, just a quick overview. All we, as I mean, like most of us know, RDBMS database is a relational database, and it has data very structured.
A little bit on the load balancer, if I have not covered already.
Actually, I have covered about load balancers in the previous session. I think session 1. You can actually go through the in the part 1 video.
Yeah.
So yeah, if not, like I'll be happy to answer some questions at the end if we get time.
Sure, thank you.
So the quick overview of like RDBMS, like everyone should definitely be aware of ACID properties, which is the main drive behind using RDBMS. So when we say ACID properties, A stands for atomicity, whether your transaction does happen or it doesn't happen. And consistency, every time you do some update, it brings your database from one state to the other. And they're like isolated, which means that though you submit a batch of requests, it'll have the same effect as they will be executed in serial fashion. And durability, which means that like once a transaction has been committed, it will remain so. I mean, like let's talk. The main intention is to talk about the techniques that we want to use for databases to improve their availability and scaling. I mean, like, so these are the 5 or 6 different techniques using which we can scale the databases. So the last one is basically mainly on SQL query tuning and that kind of stuff. But like, let's jump into the replication. The first 2 are based on replication. So this is just one diagram replicating like different patterns that we have. So we'll go in detail about these techniques, how you want to scale databases. So the first technique is just a minute. Okay, the first technique is a master-slave replication. The idea here is like, instead of having one node, like you will have one master node and 1 or 2, or you can keep adding slaves as many as you want. But depending on, like, you need to judge how many slaves you really need based on your user traffic, read-write ratio traffic. Like, so maybe it will be, the reads will be 10:1 ratio or 100:1 or 1000:1, like depending on like what kind of scenario or the application usage that you look into. So based on that, so the idea is that the master would only serve the reads and writes, and the slaves will only serve the reads. So thereby you are offloading some traffic on master, which will only take care of the writes. And as and when the writes come to master, it will have a mechanism to replicate the data into slaves. So most RDBMS like MySQL, Oracle, SQL Server, Postgres, I think all of them support this master slave replication models. So all you need to do is simply say like you want to have master slave configuration, and it will take care of the replication for you. So since we have one master here, if suppose if that goes down, so you need to have some logic for the slave to get promoted to the master. That means most likely like the slave will need to take over the master IP address and declare itself as a master. So suppose if this master has gone down and if we promote the slave 1 to the master, it will have one master and one slave, and it can still serve the user traffic. And meanwhile, you can begin to see what caused the master to fail, and you can get that up and running and have that back as a master or even acting as a slave until like another system goes down or something. So the only disadvantage here is like the additional logic is needed to promote slave to master.
Naga. So do you really need to configure the slave as the same IP with the master, or if you just change
no.
DNS is okay? Yeah.
No, they will not have the same. Either one works, but it's typically if changing in DNS is a bad idea, because this DNS servers, how they behave, right? Like they typically cache your IPs for a day or like for hours. So until then, like it will be keep hitting the same old IP. So imagine if you have like one IP for this master and another IP for slave. Even if you change in DNS to point to the slave, so what would happen is some requests would keep going, because even browsers can cache the IP address for the first time. Only for the first time, if they don't have a local cache, they go to the DNS, and once they get it, they'll have each DNS server will actually respond with IP address and its time to live record. So basically, the time to live can be an hour or 2, and until then, like the whichever system calling system can cache that. So the request will keep going to the same IP. So we need to promote slave to the master and have the same IP as the master, only then I mean like it can continue to behave in a good
How does
responsive
that
way.
happen? Like who takes care of changing the IP addresses on the fly?
I think you can have configuration because I mean like I think databases support that because the fact that they have the clear patterns for this replication. So all RDBMS support this kind of a setup, and as I said, like there is a little logic. It can be a script, like maybe some DBS can write a script to as soon as some heartbeats of master is, I mean like it's down, I mean like as long as the notice, this can itself try to take over this master's IP address and declare itself as a master. Any slave can do that, and let's say like the slave 1 does that. So there will be typically it's a configuration based, and mostly like the DBS should be able to do that automatically using some scripts. So I'm not going into detail how we do that, but I'm saying it's possible in automated fashion also.
Okay.
Can you use a load balancer here, Naga?
Yes, I will tell like how we can use load balancer. So the problem here is like it is good you are serving the read writes here and reads on the slaves, but like if the master is down, then you're having the writes till the slave is promoted to the master. Your rights are lost, right? Like your system is not able to serve the rights. That's not typically a good way to design, because our system should be always ready to support rights also, even if the master goes down. So what we need to do is generally add another. I think I can go on to the next one, which will solve this.
Yeah,
purpose.
Before you go in, a few quick questions from the chat room. One was around saying, what is the heartbeat leader direction logic? I think that's a fair bit more complicated, so I think we'll skip that part. The next question was like, what do you mean clients have direct access to database? Don't you have like a layer of abstract or proxy in between? So that way you'll have like a web service is the only one that will talk to the database. And don't you have like a business logic layer in between? What do you mean by clients talk to the database?
Yeah, so I mean like this is just for us to understand, but like in reality client is not directly talking to the databases. They're coming through a layer of proxy, I mean like reverse proxy or load balancer, and then your web servers, and web servers could talk to application servers or it could talk to the databases depending on the kind of the architecture that you have. So if you haven't looked into the big picture, I can just quickly show one of the big picture architecture. So if you see here, this could be a typical architecture that you have. So this is covered in part 1. You can actually go back. So we are just going to one of the topics in this system design. So you can see a load balancer exists, write exists, and then you have different API server. There could be like a different microservice API servers, web servers which are serving the traffic, and they are the ones which will talk to your databases.
Correct. No,
it's not a direct.
Even when you say client, you're not talking about the end user or the person who's actually visiting your website or your application. But it's actually a bunch of different services underneath. The services are the clients of the database. So if you have an abstraction layer that he's talking about right now on the screen, so there will be that. It makes sense. Just one more quick question, which is on a slightly different tangent, Naga, was that would it not be possible to like force a cache refresh for the new IP when you're trying to promote, like if the IPs were to change? The short answer for that is that actually no. The DNS cache is something that you don't really control. The IPs get cached at various levels. The general expectation is that if you have a time to live or a TTL, most systems are expected to honor that. but there are like quite a lot of weird things that happen at times. When I believe like there are versions of Java applications where once you do a name resolution, the thing remains cached forever unless you restart that system and things like that. So a lot of different systems are involved, and I don't think there is one magic silver bullet that can refresh all the caches. So there is the smarter thing to do would be to leave the IPs as is and just like flip the routing underneath the system. So that's why you're saying let's acquire the master's IP address and then give it to the new master, so that all systems are just to go much easier that way.
Yeah, just wanted to clarify on the IP address change. When I say like we are only changing like if this is 10.0.0.1 and this is 10.0.0.2, so since the master went down, all we are saying is like since that server is anyway down, that IP is not accessible. All you are doing is just map that same IP like 10.0.0.1 to this slave, and I mean like this still supports reads and writes, and I mean like even if the client APIs are still accessing that the slave being promoted to the master, but it also supports writes. The fact that though we say it's as a slave, it's almost the same replica of master, except that it's being used only for reads at the moment. So, but it can be used. So here the clients on, I mean like clients are your internal web server or application server APIs, which are basically calling the database, right? So they know like when like some system is down or something, like you still are able to access the master. Hello?
So Naga, I have a clarifying question regarding the same thing. The changing the IP address you mean is any packets in network, any packets coming to that particular IP address, once the master is going down, the packets will be redirected to the slave machine instead of the master machine, right? Internally, that's how it will work, right?
No, I mean like really I think what I say is those packets will be lost as long as the master is down, and like the time taken for the slave to replace the master and declare itself as a master. Imagine if you take some 10 minutes to promote your slave to master. For those 10 minutes, your since master is down, any packet sent to that IP will be discarded. That means like you are not serving those user requests.
Yeah, so, I can understand. Actually, I am not able to understand the concept or the term you are using, like promoting. What it mean by promoting the slave to master? Because what I understood or thought is like once the master is not responsive, maybe the heartbeat is not responding or something like that, automatically the network will take care of routing those packets to the back, the slave system, something like that. Is that not right understanding?
Yeah, it's basically, since I don't have the big picture here of the architecture that's why it's causing the confusion. But if you look into the big picture, like if you have multiple servers, you typically have a load balancer redirecting the request to slaves or master, depending on whether it's read or write. So since that knows that the master is down, like you can have the configuration, it could be the two way. Either you can have a setup in this master slave itself, like the promoting slave to master, or you could have the logic in load balancer itself, since the master is down, redirect all the writes to the slave until we get a heartbeat reply from master.
Okay, yeah, I got it. Thanks.
So yeah, the main intention is just to understand what this technique is. Like instead of having just one database serving all the requests, this is one pattern of having a replication, and it supports, like now that you have 2 or 3 copies. So this number of slaves and masters is depending on the size of your, I mean like the users, or the like as and when it scales, this number of masters and slaves will keep increasing. So let's quickly get on to this second one, which is master-master replication. So if you see the drawback of the first one, master-slave approach, you are not serving the rights for a certain period of time. That period of time is the one which takes slave to promote itself as a master. But in this case, you will have both masters, two masters, and both are serving reads and writes. So, and here a scenario is like each write that you do to any master, it will have a synchronously replication mechanism to other masters, because the because like even if somebody reads on the second one, another master instead of the first one, it should be able to have the previous latest updated one, right? So here with this master-master replication idea, so though one of the master goes down, your system is still supporting both reads and writes, and you can still combine this both master-master replication and master-slave, this one and this one. So you can have a slave attached to this master and slave attached to this master, and have all the reads go to the slaves only and writes just go to the master. That is also possible. So for each master you can still have another master slave. So that is basically you are just having this multiple times, because having a single master is again a single point of failure. So,
okay. Maybe
so
now I understood your point. Maybe I confirm my understanding. The promote you mean is maybe the slave is not capable to support the write at all. We are promoting means we are running some extra logic on the slave to make sure it is capable to support the write. The time period only you are talking about, right? The promoting time period, it may lose some packet, something like that. Is that right?
Not really, but because all slaves will have the same capabilities like master, because they are just replicas, but they are designated to serve only reads. So only designated. So when I say the promoting logic, because you know that your clients, which could be the load balancer or your application or web server APIs, know that they need to reach to the slaves for read and this. So the moment when you want to change this setup, right now, you have told earlier that your slave is serving the read. Now you are saying one of the slave needs to take up the write responsibility also. So you need to have this information update passed to the client.
Okay. Then it's just a configuration change only. Database side, everything will be capable for everything. Okay.
Yes. So database side, everything will be capable. It's just the configuration scripts that normally DBS will have to promote.
Okay. So whether you are having master or master slave, still the database wise both are same configuration, same capability.
Yes. It's just a way of Yeah, it's a general observation that like even if you take Twitter or Facebook, so the amount of reads, people loading the tweets or their timelines is much heavier than like the people actually posting the tweets than like, or actually posting some Facebook posts. So if you compare the read and writes, the reads are always on the higher side, and if you have this differentiation between the writes and reads, so I mean like you're controlling, you're making your system more available, and your masters can only take care of the writes and if needed, and you can have all the slaves do the reads also.
Okay.
So,
but it will add more latency, right? Because you are writing everything in your master. RDBMS, everything running with consistency, right? Here, consistency generally will be more important, right?
yes, because yeah, and all RDBMS support very good replication mechanism. So they come with inbuilt replication, this all master slave, master replication setup. So
okay,
all you need to say is
if those much replication everything is available, then what is the problem in scaling? Do you have a separate slide for that? Maybe you are covering that part
for
later,
what?
or scaling, because the NoSQL evolved more.
Yeah. So when I'm saying like when you introduce instead of one server, you're having two servers now doing both reads and writes. So you are replicating your database into two, right? Which means that you're like a single server handling 1,000 requests. Now if you have two, it can handle like 2,000 requests, right? So you are scaling with this replication mechanism.
Yeah.
So this is a
my question is, if it is really capable to do scaling, for example, one server you are supporting 1,000, two server you are supporting 2,000, like that with SQL also we can try to scale and accommodate, right? Because of mainly because of scaling issue only the new NoSQL and all evolved more, and it's taking dominant role compared to RDBMS now, right? Is that right, or I am understood something wrong?
Yeah, we will get into the comparison with NoSQL little later. But like it depends. Nowadays even like most RDBMS, I mean like we have different other techniques which we see in the next slides, which will help even RDBMS scale to full large user loads. Even the top companies are still using RDBMS. They use NoSQL for some section of only if their data is different or not really structured like tabular formats like RDBMS.
Oh, thanks.
Yeah. So here another thing is.
Yeah. So let's say in this case, two masters case, if the same record is being written by two clients at the same time, how does that synchronization happens? Let's say if client one is updating record 100 and client is updating same record 100. So how does the synchronization happens between these two? They both might be different data.
Yeah, that's a good question, and I was actually about to come for that. So whenever some write happens to the master, so it will not respond until it syncs up with other master on the write. So that means it synchronously updates any writes coming to this master to the other master. So even if client 2 sends to another master, which is 2, by the time it already has the previous update from master 1. So that's why in the disadvantages I mentioned, like there will be an increased latency to respond to writes because they need to be synchronized. So, and it's master responsibility if you add slaves here. So it's master responsibility to replicate to the slaves. So all the masters do is whenever some write comes, if there are 2 or 3 masters, then they need to synchronously update all the masters. And similarly, even if you have more read slaves, it also increases latency because they themselves will still need to replicate to slaves. So which means that the write performance will have a hit. So that means like the latency will be little more. Okay. So this like the first disadvantages is basically if you have 2 masters and you typically need to have 2 or more than 2 masters, you need to have a load balancer or some kind of application logic if you want to have that from your application APIs only to determine which master to write. So you need to have that mechanism, and it will have a latency. The general disadvantage of replication of both previous and the current one is so if one of the master fails before sending the right information to others, then there is a potential loss of data. Suppose like it has got a write request, but this was down, so that interim time, like there will be a little time where you lose some of the writes. And if you have in the master slave model, if you are having more slaves, since what master does is it sends a bunch of writes to the slaves, so which then apply on themselves. So if there are a lot of bunch of writes happening in the master and they go to the slave, so since they need to reapply each one by one, so it could affect some of the reads that it's serving. So it might serve little lower read count than it's supposed to.
Hey, Naga, I have a question. When you have master-master replication, how the database constraints are handled? Like, for example, if there is a composite primary key set based on combination of fields in a table, like if there is one such update happening in master 1, and if there is a similar update happening with through a different client to master 2, how that database constraints and consistency is handled?
Yeah, I mean, like that consistency is that's a capability of RDBMS, right? Like when a write is happening to this master, if you haven't followed the previous talk that I was, I was just clarifying the previous question, right? So if you write to the master 1, let's take this master 2. So you're doing user 1 is doing write 1 on the same object. So before the user 2 submits to this master 2, they will have the information from master 1, and this master itself will have that update if this guy submitted first. If this guy submitted first, this update will be there in this master 1 before this write happens, because before this masters respond on writes, they themselves replicate to the other masters before responding saying that write is successful.
Okay.
So that's how they'll have the latest ones before. So it's as good as just serving a single transaction commit once it gets the write.
And when there is an update happening on one particular record in master 1, like will there be a lock on that record if there is a similar update request happens on the same record through another client through master 2?
Yeah, I mean, like when I say writes, it's all except read, all the create, update, delete, right? So since it synchronously updates to all the masters in that boundary, in that all the database servers, whichever is master, it synchronously updates to all of them, which means that if somebody is doing here, then this master is already aware of that, because before this guy responds to the client, he has already replicated that create, update, delete to this other master also.
Okay.
Okay, so let's get on to the other scaling techniques. So another important technique to scale databases is like you split the databases by function. Say like if you have in this example, if you take like you have forums, you have users, you have products, each one is basically serving a different data together. So all these databases support only have users information, store user information. They serve only user requests. And so similarly, this supports only products related information. This supports only forums related. So the idea is like if your business is like if it's an order, if you have like a typical e-commerce website, you basically have orders stored in one database and products stored in another database. And like, so similarly, all the bills or payments could be stored in another database. So it's basically by functional domain, you can split the databases, and each of one of them can still follow master slave model or master master if you really need to support a large scale, like in the terms of Twitter or like Facebook. So each of them can still have two masters or two slaves, depending on the amount of traffic. I mean, like if yours is a really small, then it's as good as that you can have one master, one slave, or simply even one database. Like if you have only one database, the thing is it will become single point of failure. So that's why it's at least good to have two of them doing like two master, which supports both reads and writes. So the benefits, as you see here, less read-write traffic to each one of the databases. And since you are replicating only forums data here, so the lag will be less. And since they're all in like in two different, different servers, they can more data can be fit into memory. So writes can be parallel, like that means like if you have some 2-3 one composite request which could write data parallelly to the forums, users, products. And the disadvantages of like if you do this federation is like you should have some mechanism to join the data from like all these databases. So basically the reading will become complex. And your application also should have logic excuse me, to write, like to know where to write. Excuse me.
Any questions so far from anyone? Like, let's give Naga a minute to catch his breath. I think we are like somewhere at the 1 hour mark right now. So any questions from anyone?
Yeah, I'm just curious about the Twitter feed actually. So if there is a live meeting like one.
Sorry guys, I'm back.
Yeah, so let's say if there is a live meeting like some president's speech or something, if people will be commenting so many stuff, right? So how does that kind of, so many rights will happen and then globally available at the same time, like different geographic locations, how does this thing happens in the back end?
So yeah, so what would normally happen is like for this event-based load, so to support this, what we normally do is like the auto scaling. If you have used some AWS or some another Azure or some cloud, you might know about this auto scaling patterns. So you say that like if your current servers load on, like if you take about this databases, if you see that like the current server loads touches like 80% and above, it's more likely that you might need more master like to support writes and even slave. So you could basically have a replica. If you take this as a tweets DB instead of forums, you can actually have this master slave as another master added here and another slave added here. So and it could, and you can update the same thing in your load balancer as and when you add that server. so that to distribute that. So all these auto scaling patterns are supported in most of the cloud databases. I mean, like if you configure in the cloud, you can have the patterns, this event-based patterns determined, and automatically bring up a new server as needed. And when that event is done, it notices that that load is less, so this set of servers are enough to handle the load. So, and they can respond. Did that answer your question?
Yeah, I think kind of. So another different part that I had was like, let's say different locations, right, geographically. How fast that thing can happen, and how to make sure your live feed is not lagging because of that widespread synchronization.
Yeah, I mean, like
people follow.
Yeah, I mean, like the geographical based, I think I already covered in previous, which is basically you explore the using the CDN, and you can also have more cache servers, and depending on the region, if you know like more requests are coming from the US East Coast, you can leverage, like if you know the AWS, they have this region based database, like region based services. So they have the server or data centers in US West, and even in the West, they'll have multiple availability zones. Like each availability zone is a kind of a data center. So even if one data center goes down with some power or some calamities, like even there will be some other availability zones within the US West supporting that. So this replication will normally happen between these availability zones and between the regions to support the traffic from, say, if there is a user accessing from US East Coast, he will definitely hit a Amazon server in US East Coast in one of the availability zones near to him. So that's basically determined the nearest IP and the nearest content could be identified with the help of a DNS.
Yeah, that is understandable for the normal usage pattern. I'm referring to the same use case where like there is a live feed happening, and then like making sure that live feed is synced across all different regions, and then that sync should not cause the lag in the live feed if anybody is trying to comment or something like that. So that kind of scaling, will that work with the similar settings, or do we need to make any special arrangements for that? I know like you already covered one thing like auto scale pattern based on our event based auto scaling. Other than that, do we need to do anything else?
Yeah, I mean, like since if there is some kind of I mean, like we could definitely do something in prior instead of relying on auto scaling, because auto scaling typically has some little kickoff time using which I mean, like upon which it normally is able to serve the full load. So if you know upfront, you can very well get ready with a more replication, like with more set of servers. Like, so let's keep RDBMS outside. So even if you want to support like multiple writes and other stuff, you can have multiple different caching servers sits on different regions, and they could have asynchronous event based updates, which I will actually go through. There are like various caching mechanisms. I think this will be a good candidate after we complete the caching. Do you want to hold up this question? Because I'm going to cover that.
Yeah, go ahead. Thank you.
So, any other questions? So let's quickly go to the next scaling technique. So since we have talked about federation, which mainly splits the data by business or function, so the idea of sharding is that you you store like you here also you do the similar splitting, but instead of splitting by function, you actually split a subset of data. Suppose if you take the user example, you could have 4 different databases. Like the first one handling the A to C. When I say A to C, it could be the last name. It means the last name, which later it starts with. So if any user's last name starts with A to C, then I put him in first database. And if anywhere it starts with from D to F, I put him in the another. And similarly, like this is just an example. And if your data is really large, you can have more set of databases serving only that subset of data, and you can have a load balancer known that only the first database here knows only like A to C, so forward only the username starting last name starting with A to C to the first one. So similarly, like all this subset, we let the load balancer know so that it routes read or write request accordingly to each of those databases. So benefits are like similar to the federation. So these are some common ways to shard, but like these are not the only ways. It depends on your business needs. You can define how you want to split, how you want to shard the databases. You need to determine. So some of the common ways is like based on user last name initial, and it could be based on geographic location. So this disadvantages like are similar to the federation because you need to have some application logic in like load balancer to know like where to write. And if you want to combine the data, like if somebody is querying the data from users, all the users which fall into this multiple databases, then you will end up with complex SQL queries. And another disadvantage is that though we split by this range, there could be so many users, like say within users A to C, so which is like you are overloading this one part of databases. There may not be many users in users D to F, so you need to carefully choose which subset and how much of data it normally handles. So that will result in increased load in one of the database compared to others if you don't watch for that. And the joining data from, as I said, like the similar to SQL queries, joining the data gets complex if you want to combine the data from multiple shards. Any questions? And one important thing, like before moving ahead, is like you can combine this federation and sharding techniques along with the master and slave. So like if you have a user's database here, it can have this master slave or master approach. So the same thing goes here. As I said, here also, as the example shows, it has this master slave model. So you can combine any of these techniques with master slave or master. So depending on your needs. So let's get on to the last two techniques to scale databases, SQL databases. So they are like denormalization and SQL tuning. So remember I was saying like both for federation and sharding, it has to combine the data from multiple shards, right? Like you are making the read quite complicated here. So but you still, I mean, like you cannot have everything in the one databases because as and when your data grows, even if you do the replication, each of those servers become quite big enough so that like so you should not, RDBMS cannot handle quite large loads. So it's good, it's typically you do either federation or sharding to split the data and apply this master slave, and along with that you will also denormalize the data to improve read performance. So when I say denormalization, what you do is you will have some databases sitting next to here. Suppose I can say I can have some users read database which can denormalize, like read the data from all this and update into that other read database, which can serve the reads quite quickly. So some of the key databases like Postgres and Oracle support some concept of materialized views. So which is basically if you are doing some complex joins, since you know that it will result in expensive read. So what you can do is you can create some materialized views which saying that this view needs to pull data from this shards or this federated databases. And what this like in this scenario Postgres or Oracle does is that as and when you write to the main shards or databases tables, it will also update this materialized view as long as that update, like as long as that columns or that rows touches something in that materialized view. So when I say denormalization, you are basically introducing the redundancy of data by storing some specialized tables to support the reads in another database, and you have the reads go to those denormalized views. So as I said, like it can become, this technique can be combined with federation and sharding to overcome that complex joins. So as I said, the general read to write ratio is similarly like 100 to 1, it could be 1000 to 1. So it's always good to denormalize the data if you are splitting the database using like federation and sharding. So the last technique is using SQL tuning. I don't have much of content. I think there is a lot of ways you can tune your SQL queries, tables. So I just kept a quick pointers here. It's not like we're not going in depth because it's all, I mean, like it's all like all the information is well known. Like you can go and look in like how you can tune the queries. The quick ones, like you need to have a very good schema. So suppose when I say good schema, some of the examples are like if you know your length of the column data or like of the person name cannot exceed like 50 characters. So it's as good as that you define using char instead of varchar, because when you say varchar, the database needs to database will configure that column in a different way, supporting up to 256 or more. So try for a less or more known, more restrictive data type as possible. And use text. I think it's a there is a use text for large content, because if you use there is a spelling mistake here. So when you use text data type, it will have a some pointers to a text or content stored somewhere outside. So the performance will be better, and declaring wherever not null possible. And you need to have good indices, basically on the columns that you are using in select, group by, order by, or whichever the ones that you use in joins. So they improve the performance. So with that, we conclude this scaling techniques. So before going into the NoSQL, any quick questions? Sorry, I'm not actually keeping track of the chat.
That's okay. There are no additional questions in chat. People have been discussing. Any other questions from folks?
Okay, so let's quickly. Oh, somebody was asking in.
No, let's go on. Nobody's asking. Let's move on.
Okay. So let's quickly, I'm not going in depth on NoSQL because each of the databases can be drilled in depth. So I'll quickly cover like what NoSQL is for and why we need to go to NoSQL, and we will also compare like in the next slides with RDBMS, when you need to choose RDBMS and when you need to go for NoSQL. So basically, when you say NoSQL, it's basically non-relational data, and semi-structured non-relational data is mostly a candidate for NoSQL. And these are some of the types of NoSQL databases in use today. So one of the famous is key value store. These key value stores are quite popular in terms of caching or distributed cache databases like Redis and Memcached. You can even like, they need not be even cache based. Like I think even DynamoDB supports key value based as well as some other type of data. I think document type also. So I think they mostly place a very good use in the caching databases. That's why I given a caching databases name here. Another type of NoSQL data store is documents. So some of the popular document-oriented databases are MongoDB and CouchDB. So when we say a document, it could be a JSON document or XML document, which can contain some internal structure. Like this document could further leverage key value pair to store the data, and that's what they do. And there is a white column store. So again, you can go and see what a white column store is. I didn't want to go in depth here. So some of the popular white column store is Google Bigtable, Facebook's Cassandra, and HBase from Apache. And another popular database are like graph-based databases. They are not quite old compared to the other first three, but they are slowly, like I think recently picked up. I think people started using those graph-based databases. And all this kind of databases, most of them favor eventual consistency. That means like if you make an update, it's not guaranteed that the next read will get that, but eventually it will have. So that's why it is most of them favor eventual consistency. So there is a good acronym for this, like which is BASE. It's called basically available, soft state, and eventually consistent. So most of NoSQL databases typically fall into this BASE type of architecture. So which means that if you look into that CAP theorem, consistency, availability, and partition tolerance, you have to choose between consistency and availability, right? So this BASE typically chooses availability over consistency. So, and consistency guarantees in the form of eventual consistency. And soft state, it means that the state of the system changes over time, even with or without input. So that, let's quickly head on to the comparison. How you want to compare this NoSQL and SQL databases. As you can see, like the SQL like is always structured tabular data. It has a strict schema, and all data from one table to other is related. So, and you have clear patterns for scaling, and you know that when you want to choose RDBMS, there is a need for ACID properties, right? Like it needs to either respond, it needs to either do it or not do it, that kind of a thing. Like we already went through this ACID properties. So whenever you see a kind of transaction-based systems, like maybe a payments kind of a thing, where there is a clear need, or So typically this financial related systems need to adhere to ACID. So there is a so that's a good candidate for RDBMS. And we know that if you know it has a strict schema and the schema is not changing more often, then it's a good candidate for SQL. And whenever it's a semi-structured and if you know the schema is constantly changing, then you can pick NoSQL. And if you know that there is definitely going to be large terabytes of data, then RDBMS are not quite good at handling as the data grows. If you need to support that, you need to follow those sharding or federation techniques combined with others. But like NoSQL, they're basically available. They themselves take care of even if the data is quite large. So even if the data is very quite data intensive workload, you can go to the NoSQL. Any quick questions? I think we might head to the caching next. Assume no. Okay, let's head on to the caching.
Quick question on like a couple of questions here. So one was around what do you mean by basically available? Is there like anything specific with the word basic? Why do you say it's basically available?
So I think it's mainly concentrate on availability. It's when you say basically available, it means that it's always available or mostly availability. So your system is guaranteeing the availability. Since it's just an acronym, I think I don't know why. I mean, like since they're basically available, maybe I don't know. That's why I choose basic.
And, the other question was the soft state that looks like it's the opposite of the durable in ACID. Is that so?
Yes, because durability, once something is committed, you know that it's committed or not. I mean, like, but here, I mean, like, since there could be, since it's not guaranteeing durability, that's why it's said soft, not hard state. It's kind of opposite. Yeah, you are right in stating that.
Got it. Let's move on. Thank you.
So yeah, so caching is a very important concept, and it's a very one of the important technique if you want to scale. Hello? Yes?
Yeah. So you said like something on graph database, right? Can you elaborate a little bit? Like I did not quite understood what is that means there.
Graph database is basically let me quickly see if I can show you in pictorial, though I don't have any code. I can quickly show, I guess, if I have. Just a minute. I hope you're not seeing my screen. How can I share? Let me see what select items to share. I'm sharing something else. I mean, like though it's not there in the slide, you can actually go through the. I mean, like then I have shared a reference of this link. You can go through that. So, can everyone see my screen?
Yes, we can. Thank you.
So this is a example of graph database. As you can see, there is a one person, like it's basically a kind of social network, right? So building the relation between, like one person can have relation with multiple nodes, and each of them can, like if you see in this case, this guy knows this and this, and the relation is knows and since is this and the ID is this. So it's basically like if you really picture a graph, and if your data really looks like that, then mostly graph databases are a good candidate. So I think like if you know about this friends circles. I think they will be one of the good candidates for graph databases. And similarly, I can also show wide column databases. When I say wide column, this is one of the super column families like called companies. So all this is a row, even though it has this address and website. All of them are classified into row key 1, and in this row key 1 there is a column family called address, and there is a column family called website, and each of those column family will have this key value pair kind of thing, like city and value is San Francisco, state and California, like this. So each of this pair is actually column. So it has a name and value, name and value. So this is just an example of column databases. So let me come back to this. Are you seeing my screen now?
Yep, it's a presentation. Go ahead.
Okay. Yeah, thank you. So yeah, that's just a quick overview of the white column and graph databases. So let's quickly do the caching, and I also have some another concept. I doubt I can cover that. I'll probably cover that in another session. So let's try to complete the caching in another 30 minutes. So caching is a very important technique if you want to improve the performance, mostly read performance. So there could be a different type of data that you want to cache. It could be static, and if it's a static content, it's a good candidate for CDN caching, or even reverse proxy can handle that. So CDN is something sits to the closer to the user. So basically, like if user is sitting in India, there will be a CDN location near to that. So if you upload the static content into the CDN, he'll be able to quickly see that. So similarly, reverse proxy also can support static content as well as caching dynamic. Like even the read content, like your server responses also can be cached. So some caching can also will be done by browser and OS. So as in that you can notice when you are visiting some websites and they are like static. So it's mostly browsers and OS also will cache those images and JavaScript files and all. So another place of caching is database caching, near databases, and application caching. So when I say application, your application maintains this in-memory cache, like Redis or Memcache. You can also cache at database query level and object level. So these are all the different places where you can have the caching. So as you can see, this is a typical strategy of caching. Whenever a user or client requests, your dispatcher could be anything like reverse proxy or load balancer, or even your application. This dispatcher could be anything which is handling the cache. So it looks up in cache. If result is found, it simply responds to the client. If not, it forwards to this worker nodes, which could be any of this, depending on where the caching is. So they improve the page load times, which is basically less latency. So it reduces the load on servers. So those are the main key benefits. And with that, let's get into different caching strategies, different caching strategies, how you can implement this caching. So one of the first strategy of having a cache is termed as cache aside. As the name itself says, you keep the cache aside, not in between your client and your storage like database. So when you have the cache aside, whoever is calling basically in this client will first look into the cache, and if he doesn't find an entry, then he queries the data from storage or database and puts that entry in cache, then returns the response, like so return that entry. So it's basically for the first time it will have one entry finding a mess, then get the value and put it back. So the subsequent reads, when it hits the cache, if the entry is there, then it directly gets data from there. So here who are calling like the application is now responsible for reading and writing to the storage. So in this case, like as you see, cache is not interacting with the storage. It's basically the client who is doing that. So this client could be your application, or it could be a direct client who is consuming. So the disadvantage with this approach, as you see, for the first time, there will be 3 trips. First, finding a cache miss, then getting the data and putting it back, and then returning the entry. So, and there is another issue, like if you put something in cache, and when you look into that and you simply return, and if you have in the background your application has updated some data in storage, so your cache might still not have it. So that's one drawback. And how we mitigate that is, like whenever we put some entry in cache, excuse me, it also we also put against each entry how much time it has to live in the cache. Like say it could be like 1 hour or 2 hours, depending on the frequency of data change that you can judge. So until that time to live, user may be reading in old data. So once the TTL is there, it will be discarded in the cache, and then it will again be like a cache miss. So he will read again and update entry next time. So if something happens with the cache node, it will be replaced with some empty node which will not have any data. So it's as good as again like going for 3 trips for every record for the first time. So that's the cache aside. This is a simple strategy. You can say it's not much in use. Maybe it adds. Maybe there are some use cases for that, but I can say this is not quite widely in use. So let's go to the next strategy, which is write through. So in this, as you see in the picture, every write will actually update the cache directly instead of directly updating in the database. So the cache will need to take care of updating the data in database. And once cache updates the data in database, you return back response to the user. So as so the disadvantages here, as you can see, excuse me. So when a cache node is created due to failure, that means that you already had some cache, and if this was created newly, or if you add some new cache, then this will not cache the entries until you have the subsequent reads or writes. So for this, like you can also use cache aside, and sometimes like though you write data to the cache, not all data can be read back by the user. Suppose if he is writing some 100 records, he may be reading back only like 2 or 10 of them, not all of them. So in that case, you can, every time you write some entry to the cache, again you can use TTL, time to live technique, to get to discard the request from cache. Let's quickly get on to the another technique, so which is a write behind. and this is a little better technique than the previous one, write through. In that, why I say a little better is like, as and when you write an entry to the cache, it will add an event to the queue. So in the previous technique, if you see, it's waiting until the record is entered into the DB, and then only it responds to the user. So it's basically synchronous. But here, what it does is, like, as and when you write to the cache, it adds an event to the queue, and as soon as it knows that it has confirmed, it created an event to the queue, it simply responds back to the user. And there will be a separate event processor which will keep polling the queue and see if any write events are there, and it will asynchronously select the items from queue and update the database. So only thing is, in this case, as I said, like, since you are adding this queue and event processor, it will be a little complex when compared to the previous two techniques, because you are adding this extra overhead. But I can say it's a good technique. And there could be a data loss if cache goes down. So if this goes down prior to hitting the queue, then you are losing the data. So basically, to overcome that, you again have multiple nodes, like similar to the replication, like a distributed cache. In that case, even if one of them goes down, the other nodes will be available to serve the request. The last technique or the last caching strategy is like you put cache in front of the storage, and what you do in cache is, like, you will have the cache automatically predict which entries are needed by the client. So this is basically a prediction. So if you know there are like some set of data which is more frequently accessed, you can get that from the database upfront before even the client requests for those records, and have it in cache. And so when a client sends a request, you have that data upfront, so you can respond back quickly. So the key disadvantage of this approach is, if you don't accurately predict, then you end up storing some junk records which are not accessible by the client. So thereby you end up hitting storage every time. So which will again reduce performance. So if you are able to accurately predict, then I think this will be a good technique. So as the name itself says, you are refreshing ahead of client invoking for that record. So in general, the disadvantages.
Quick question.
Yeah,
Ram's question is, I assume the cache size is partial to the storage, so there will be logic to pick the last n writes to the cache. Am I right?
Yes, because whenever we say cache, it's not as big as storage, which is physical storage. When we say cache, it's basically sitting in the RAM, right? So the cache size is always limited, and so you need to have some strategy to predict only the items which can fit into the cache size. So if you say a cache size of 1 GB and your database store is 100 gigabytes and cache is 1 gigabyte, then you need to predict items which are good enough to fit only that 1 gigabyte. Or if you have 10, you need to fit only the ones. You need to select the item such a way that it only fits the cache size. So with that said, like, if there are some like more frequently accessed, then the previously selected items can be discarded. So that could be one technique. So with this technique, you need to keep monitoring and revise your prediction strategy depending on how the reads are coming. So in that way you keep refresh ahead like up to date. So if you don't follow this prediction techniques, then it's as good as adding one extra hop. So every time hitting the storage and getting back. So the disadvantage of So the disadvantage of cache in general is like you need to maintain the consistency with cache and database. And cache invalidation, which is saying like which items you need to have in cache, which items you should not have. So that's a difficult problem, and you have various strategies like least recently used, most recently used. So some of them work best, but still like not 100%. So cache invalidation is a difficult problem, and you can still deal with that. But it will have some complexity. So, and when you have cache, you need to have your application logic to look up the cache first, and then go to the database if not found. So you need to have some application changes if you have cache. So any questions on cache so far? I quickly went ahead, I guess.
A quick time check. We've got about 15 minutes or so.
So yeah, I think I would skip the consistent hashing because I don't know unless everyone is willing to spend extra 15-20 minutes.
No, let's actually keep time, and then if required, we can always follow up with additional sessions at some points of time. So what I would recommend is close what you have as topic in the next like maybe 10 or 12 minutes, and then we'll leave about 5 minutes for questions in there.
Okay. So let's quickly head on to this TCP and UDP. These are one of the important protocols that you should be aware of in general. So this sit in the transport layer of OSI. If you have, I mean, like if you see, let me quickly show up if for those folks who have not seen it. So this is our OSI layer, if you like, which is to depict the network's communication channel. So if you see, there is a transport layer. So both TCP and UDP sit in this transport layer, and both use IP and the lower channels for communication. Let's come back to this comparison. So the TCP, when you need to use and when you need to use UDP, is like whenever you are looking for high reliability. So then TCP is a good candidate. So, and it's always connection oriented. And when I say connection oriented, like each when you send some data packets, like in TCP, the data is in the form of packets. So TCP establishes a session to send all the packets that it has got to the destination in the same original order. So, and it implements congestion control, and it's mainly used for this HTTP, FTP, SMTP protocols and SSH, where you need high reliability. Whereas UDP is connectionless. That means like here the data is actually like similar to the packets. Here they are called like datagrams. So here, since it's connectionless, they are not guaranteed to reach like in order. So they can reach in any arbitrary order, like out of order or not at all. So how UDP guarantees is only at the datagram level. And it's generally used for broadcasting, like, and it's mainly used in some routers, basically, like routers use this protocol, which internally uses this UDP. And UDP is also good for like this video chats or voice calls, streaming and multiplayer games where efficiency is more expected than reliability. So when we say reliability, like your voice should not be lost anywhere in between, or it should not be passed. So that's how this TCP works. Whenever you make some HTTP request, it needs to be very reliable that you should get a response. So but whereas in this case, if you are on a video chat or voice call, you might experience like sometimes some a pass or some voice outage or some disturbances. So this is quick comparison with TCP and UDP.
I have one quick question.
Mm-hmm.
In UDP, if the packets will not come with the same sequence, then video chat and all will be very bad, right? For example, if I am talking later is coming first, whatever I am talking first is going late, those kind of things will be nuisance, right?
So yeah, so the idea of UDP here is like when I say out of order, it's not that the whole communication will be out of order. So the sending layer will send the data like there could be some multiple intermediate nodes, right, between your sender and destination.
Okay.
So what happens in this TCP is like each node or each hop in between ensures this original order, whereas this UDP, all it knows is that it looks into the target IP and sends it. It doesn't see if the previous packet received or not. So that the destination takes care of collecting all this and ensuring of arranging back in the order.
Oh, okay.
So
thank you.
So when you use that strategy, that's how like the UDP is generally efficient. So you can do parallelization, right, mostly in this UDP. So you can keep sending. You need not wait for the previous packet if it's not received.
Okay.
So that's how sometimes you can experience those if there are some 1 or 2 packets lost or some kind of disturbance that you can notice in the UDP.
Okay, it may be more a network question, but still, if total packets is 1000, only one packet is missing, then it will still try to manage from receiver side. Still, it will try to display all the video by losing that one packet, or it will lose everything with UDP.
I think it will lose everything because that's where you'll have a pass and it will wait for the next set of packets.
Okay. Yeah, thanks.
Yeah. So yeah, with this, I think I conclude. I actually wanted to cover consistent hashing, which is another good technique, but I will probably take up that in one of the in-person sessions or another online session, which I can come up with later. So, any questions? And you can even actually go through these slides because they are very self-explanatory for folks who are like outside of Seattle. I'm definitely going to cover this in one of the in-person sessions. But like it's mostly, I think you can get a good sense from the slides because I try to be as explanative as possible even in the slides. So for the folks in Seattle, I can definitely cover this in one of the in-person sessions. So I think now we are open for questions.
Naga, I wanted to share something. Actually, I came across one technique for scaling SQL databases. So
yes.
I just want to share that.
Yeah, feel free to share. Yeah, tell me.
Could you go back to that slide where you have the master-slave diagram?
Yes.
Yeah. Yeah. So what I read is this was before NoSQL was actually built. So when YouTube was facing scaling issues or they were planning on scaling, so here this approach So they first went from went to the master slave, which bought some time, and then after that, once this stopped working for them, the reason why it stopped working for them, or it still had an overhead, was that the slaves were performing the reads. I mean, the reads were going to the slaves, and the slaves were okay serving the reads. But the QPS for the write queries, there became an overhead with the replication for each of the slaves, because it is a single thread and it is a disk-based operation. So they came up with a technique where they introduced a caching layer in between, which actually read the relay logs for the master. Like when queries come in, so there is a where clause, right? So based on logs, they populated the cache, and that cache basically, so each individual thing was not written to the slave, but it was all collected, then one IO operation or whatever. There is one disk-based operation only once in a while that was happening, so that bought them a lot of time. So I just read that, but maybe it may be interesting.
Yeah, so yeah, that's a good point. So which I don't know if I have talked about that. So though I talked about caching strategies here, so the intention is that, like here, if you take this picture, right, here you are saying these are databases, and you have some dispatcher which is sending to these databases, and you have the cache upfront here. So I think I meant this picture to be very generic, which means that these workers could be your databases, these workers could be your application servers, these workers could be your web servers. So the cache can sit in any of those layers, right? So in that in the previous case, as you were explaining, I assume like this sit ahead of the databases, so before even reaching the database.
Yeah, I think your dispatcher could be the master and the workers could be the slave, and then it would be between the cache and slaves. So yeah, I think it covers it.
So another thing is, like, these are just my main intention of having this session is just to introduce the concepts, which means that these are not good enough to handle like YouTube or Facebook or Twitter kind of a load. Each of them might have some special design scenario which might insist a need for some special kind of a technique. So we will basically attempt to solve those kind of a problems in person, like through some discussion. So whenever you pick a specific problem, like a tiny URL or like Facebook or Twitter or YouTube or Netflix, so whenever you think of designing such systems, there is each system will have a very unique complexity which are not seen in the other kind of systems. So those are all kind of different system design problems, and which we can pick up. So to even step into those problems, these concepts play a good role, like a good foundation. So that's why I wanted to cover this concepts first, and then like we can pick some problems and go deep dive and see how you can come up with such an architecture if you were to design a Facebook or Netflix or YouTube kind of a thing. Because this caching is it will become very huge if you talk about Netflix or YouTube, because you are talking about videos and there could be so many tons of thousands of servers of cache that you might need. So it's not just one or two that we are saying. This patterns, this number of servers could be like such a large extent depending on the design problem that you are wanting to solve. So any questions? So I just wanted to introduce on the concepts. This.
But Naga, do we really need to talk about this TCP UDP protocol and all in design interviews?
Not really, because it's good to know, because like whenever they get into this, how the network level, right? So if you are to drill down into some problems, like where you need to determine where like where in the network, what kind of scenarios could occur. So these are the kind of key transport layer protocols which HTTP and many other famous protocols uses, right? If you just know like HTTP takes care of internally, and if you don't know about TCP UP, I mean like UDP, so it might not be best, because like since these are very open-ended, some people might be very interested in like how much you know in terms of networks, like how the information is being sent, how HTTP leverages this TCP, and how this routers leverages UDP, and when you, I mean like there could be more protocols other than the ones highlighted here. So, and why they need to pick TCP versus UDP. So it's good to know, because we don't know what the interviewer is interested in.
True.
They can go deep dive in caching. Somebody may be interested in more in caching, so he'll try to drill down in caching as much as possible. Some person might be interested in databases and the RDBMS techniques. One person might be interested in NoSQL, like one person might be interested in load balancer, go deep dive. So each of those concepts that we introduce, like we might need to go further deep. So it's good to at least aware of the concepts first. Then like as and when you start learning more, you can go deep dive in more of these subjects.
Okay, thanks. And one more question. I read somewhere like the SQL DBs are not good in horizontal scaling. Is that true?
Not really, because when you say horizontal scaling, you are actually introducing a load balancer, and you are also, I mean like, so these are all kind of techniques of whenever you add more nodes, you are horizontally scaling, right? Vertical scaling is simply increasing the server capacity with more RAM, so it can load more data. So since all this replication, whenever you talk about this replication or federation, you are splitting, you are doing like your system, you are doing more of horizontal scaling, because you are adding more nodes here.
Yeah. And one other question is, if I am doing full denormalization, then can I achieve the same performance what we can get from NoSQL?
So yeah, I mean like it depends on how much of data, because you need to denormalize, but denormalization comes up with some of the, I mean like when you say you need to denormalize, you need to have this kind of materialized views, which are kind of another tables handling having the columns from multiple tables. So whenever you write something to the database, this databases needs to take care of replicating or updating the data in this materialized views. So if you are increasing this denormalized content, then you also are adding some of the write performance.
Oh, okay.
So
thanks.
All right, we just have probably time for one more question. Anyone with another question?
Can you hear me?
Yeah, go ahead.
Yes.
I was just wondering if you're aware of a solution where the caching and the database, they keep in sync automatically without the application. That is, I mean, a lot of the examples we saw, the application was updating the caching, but is there anything out there where the cache gets in sync with the database automatically somehow?
Yeah, so one of the ways you do this is that you have these things called write-through caches. So essentially what happens is that you talk to the cache. You don't talk to the database directly. And the cache actually subsequently talks to the database to keep the database in sync, or the write operation gets deferred essentially. So the write-through cache, as it's often called, is like a very classic way of keeping the database in the cache in sync. That's one. And the second thing would be that there are databases which actually have pre-support like supported information. So most databases have things like triggers and other things that you can run when a specific event happens, and that would automatically fire the message or event required to update the cache. So without any involvement from the system, you have different architectures or different strategies with which you can make it happen. At the end of the day, there is no magic. I mean, it's just that somebody is telling the database to change a particular value, and the cache needs to know one way or another. So either it's a database notifying the cache, or it is like a write-through system where the cache is the one that's being given the command of update, and the cache updates itself, and then faithfully passes that on to the database. So it's just one of the two different common architectures that are there. Does that make sense?
Yes. Thank you.
Awesome. So I know, Naga, you have still a few more slides to go. But what we'll do is we'll actually park at this particular point of time and see if you want to do a round 3 at some point, or we may actually just take these up as discussions in this Slack channel on design. So folks, feel free to join the Slack channel and have at it with your questions. We'll see how and when we will be scheduling future sessions for online discussions. So at this point, thank you so much. Thank you everyone for attending this. Let me terminate the recording, and then I can take more logistic questions.